Welcome to the lecture for Research Methods. I'll be talking today about internal validity, about what it is, what things may threaten your internal validity, may decrease your internal validity, and then a couple things you can do to maybe address these. Okay. We'll start off with defining what internal validity is. In the simplest terms, it's about confidence. It's about confidence in the truth of a cause and effect relationship. So it's after you've done a study, or someone's done a study, the data have been collected, they've been analyzed, and you're trying to draw conclusions about the relationships between variables. And if you're trying to draw cause and effect conclusions about, okay, well, this variable caused a change in this other variable, it has an effect, it impacts it, whatever. The degree to which you can draw those conclusions and the confidence you have in those conclusions is your internal validity. And whenever you're not so sure if, well, there's a relationship, but I'm not sure if it's cause and effect. I'm not sure if it's cause and effect in the direction that I propose, that I hypothesize, that A causes B instead of B causing A. If you don't have that confidence, then you have poor internal validity. Right? And there are certain things methodologically that can happen that will erode your confidence, that threaten internal validity. Okay. There are three basic things you have to have internal validity. The potential to draw conclusions about cause and effect, and again, the simplest here is there has to be a difference in the dependent variable, and that may seem obvious. Hopefully, it seems obvious, but this is the idea that you can't take one group of people, do something to them. So we get a group of people, we give them all energy drinks, high levels of energy drinks, and then we measure their heart rate, or how quickly they can complete a puzzle, whatever. And then if we see, okay, wow, they complete a puzzle really fast, we say, okay, well, the energy drink caused them to complete the puzzle really fast. How do you know? Maybe they're all fast puzzle completers, right? You're not comparing it to either how fast they completed a puzzle before they drank the drink, or how fast some other group of people completed a puzzle who didn't drink an energy drink, right? You have to have two measures of the dependent variable, either a before and after, before the independent variable is introduced versus after the independent variable is introduced, or between two groups. One group that gets the independent variable, kind of the active experimental level, versus some other group that gets a different level, usually the control group that gets kind of no independent variable. Not always, but usually. But again, there has to be some difference. How big of a difference does there have to be? Well, it depends, and that's where your statistics and your probability comes in, right? Because if I have two groups of people, and let's say, just for fun, that they're pretty much identical. They're as similar as I could have gotten these two groups. In one group, I give the energy drink to, and the other group, I don't. And then I measure how quickly they solve a puzzle. Okay, the energy drink group solved it faster. Okay, then I'm thinking, yeah, maybe it caused. The energy drink caused that difference. What if it's a small difference? It's they were just a few seconds faster. Well, now I'm getting less confident, right? And why am I less confident? Well, because imagine I take those two groups that are pretty close to identical, and I just measure how quickly they can solve puzzles, and I calculate an average speed for each group. I don't give either one the energy drink. Odds are that you're not going to have those two groups get the exact same average amount of time, right? Why? Error variance, right? There's variability in people's scores. And you may have a few slightly faster people in one group than the other. That day, and people may be pretty equal, but that day, one of them, one person in one group had a bad night's sleep, so they're going to do more poorly, bringing that group's average down a little bit, right? So if one group gets 4.73 seconds, the other group might be 4.6 seconds, and really, they're similar, but they're not exactly the same. There is some difference. And then your statistics typically will come in and say, okay, well, that difference isn't big enough to be statistically significant. It's not big enough to say, well, that difference is just due to the random error variance. And again, when we talk about error variance, it's not about wrong variance. It's about scores differing not because of the independent variable. So anything that's not due to the IV, not due to the treatment, any other variance is error variance. Okay. So there has to be some difference. How big the difference has to be, well, that comes into play with how big your group is, how variable each group is within itself, and then what you set your alpha level at, right? Your p-value, I say p equals 0.05, because what that p equals 0.05 is, what that alpha level is, it's a probability that says, okay, when the difference, after you've gotten the data, there's a difference of this big. You know, the difference between two groups is a difference of 1.3. Right? And you go and you look in a table for a critical value, right? Or the computer looks in the table for you for a critical value. Say, okay, is that difference bigger than this critical value? And the critical value for p equals 0.5 may be 1.0. You say, oh yeah, it is. Well, what does that critical value mean? Well, it means that if the independent variable had no effect, okay, so if the energy drink had no effect, you would expect to find a difference of 1.0, a difference of this big, a difference of this critical value, whatever that critical value is, 5% of the time, alpha percent of the time. Okay. So again, it's not necessarily, P isn't necessarily the probability to make a type 1 error. It's the probability of finding the difference you found if the null hypothesis were true, if the independent variable had no effect. Okay. So the bigger the difference between groups, the more confident we are, typically, that there is a cause and effect relationship and that it's significant. But again, a big difference, that's a really big difference, is only meaningful in terms of, well, how variable the groups are. If the two groups are very homogeneous, people in group A and group B, everybody in group A scores fairly similar to each other, and everybody in group B scores fairly similar to each other. But then the averages are way different. Okay, we have lots of confidence that those groups really are different. Now, if there's lots of variability in group A, they're all over the place. Imagine that their curve, if you were to draw try to draw the bell curve for their data, the distribution, and if it's real flat, real spread out, they're all over. Some are really high, some are really low, some are in the middle. And same thing for this group B. They're all spread out. Well, if you have these two curves and you try to map them together, you can imagine two spread out curves are going to overlap a lot more, such that people in group A and group B, there's going to be some really high scores in A that are similar to low scores in group B, that may even be higher than the low scores in group B, even though the average group for group B is higher. Right? So a big difference is important, but again, it's relative to how much variability there is in each group. So your stats will tell you that, but they can't tell you how important a small difference is, right? That comes down to what you're studying. Right? There are some things where only really a large effect, a large difference between groups is going to be important. And there are other studies, other times, situations, scenarios, where a very small effect size, a small difference between groups, may be really important, right? Think about kind of medical studies, where, okay, doing this one thing, taking an aspirin a day, if it causes this kind of slight but consistent and statistically significant difference in survival rates and the kind of likelihood of developing a heart attack, that might be really important, right? If you can reduce your risk of a heart attack by 30%, 30% sounds like a lot unless you think, okay, well, my risk is 1% and it goes down to 0.7%. Right, so that's a reduction of 0.3%, but really your risk reduction there is 30%. You have a 30% less risk, 30% of 1 being 0.3, 1 minus 0.3 is 0.7, right? That may still be important. It doesn't hurt anything to take an aspirin, baby aspirin in A. If it's going to reduce your risk of heart disease, then do it. So you have to know what you're looking at in terms of if you should be looking for large effect sizes, medium effect sizes, or small effect sizes. Typically, you only know what to look for if you're well versed in the literature and you know kind of what people have found looking at similar variables and relationships among similar variables. Okay, so it's kind of a long spiel about the difference, but basically there has to be a difference, and then currently we say it has to be statistically significant. Although there is a trend in the field to move away from relying too much on that p-value and the statistical significance and looking more at calculating these things called effect sizes, which again are ways of getting a number that tells you how big is the effect given the variability. And effect sizes, some people think that they're less easily biased by the size of your sample. Right? If you have a huge sample, it's pretty easy to get statistically significant results in terms of a p-value, but it might still be a really small effect size. My advice would be look at both. Look at the p-value and look at the effect size. So it's statistically significant, and then is it a big effect, a small effect, or somewhere in between? Okay. You have to have a difference between dependent variable, time 1, time 2, or group 1, group 2. Right. The other thing, the independent variable needs to be introduced before the dependent variable, or at least before the difference, right? You have to establish that the difference wasn't there until the independent variable had a chance to cause it. So if you have two groups, you need to establish that they're not, and you're going to do something to one, not to the other. You need to be able to establish that there's a it's reasonable to conclude that those two groups weren't different before you introduced the independent variable. Because if you kind of non-randomly select two groups. I say I'm going to look at see if this drug increases IQ, and I go I grab 20 students from MIT and I give them a drug, and then I grab 20 people who are watching the Kardashian reality show while texting and driving all at the same time. And I give the MIT students the drug, and then I don't give the other group a drug, and I test them, and I say, wow, look, the MIT students are scoring much higher on an IQ test. Yay, my drug works. No, because you have pretty good reason in that case to believe that those groups may not have been similar on IQ beforehand, right? So you have to, and we'll talk about this more in a bit. You have to either make sure that the groups are equal, or have take steps to make it likely that the groups are equal on the DV before the IV is introduced. Okay, the third thing, elimination of extraneous factors. Also, you may hear this referred to as accounting for alternative rival hypotheses. So, whenever you find a difference between groups, or between time 1 and time 2, you have to be able to account for other possible explanations for why those groups, or time 1 versus time 2, are different, other than the independent variable. And you want to methodologically have high experimental control, where you tighten your study to where it's unlikely that they could differ for any reason other than the independent variable. Like, I made sure that their experiences were very similar. If you were in the group that got the drug versus didn't get the drug, I tested you at the same time, I treated you the same way. I did all these things so your experience in the study is as identical as possible, with the exception of the IV. When the only difference between groups is the independent variable, then we're more confident that a difference on the DV is can be attributed to, is caused by that difference in the independent variable. Okay. So in theory, in a kind of ideal people-free world, because people are full of error variance, they're random and are inconsistent. But in a kind of a ideal people-free world, you could confidently establish internal validity by using either of the two basic designs we've already kind of talked about, right? With two precisely identical groups, right? Which would be when you're comparing group 1 to group 2, or group 1 to 2 to 3. You could have more than two. Anytime you're comparing people across groups, that's a between subjects design, right? And unfortunately, until they allow for human cloning, you probably can't get fully identical groups. So there's a drawback there. So then you also have this another way of looking at it. Well, I could get identical groups, at least more identical, if I use the same people and I do time 1 versus time 2. That way, your score at time 1 is compared to your score at time 2. You serve as your own control. Right? Instead of being compared to some other person in another group, you're being compared to yourself. And when we do that, pretest post-test is one type of within subjects design. So again, we're going to measure the DV, manipulate the independent variable, and then measure the DV again. Sometimes you'll see these two things combined in a mixed subjects design. When this happens, you have some interesting things that happen, which we'll see in a bit, about sometimes it's like, well, you've added both types of threats to internal validity, because some of the threats to internal validity are unique to the between subjects design, and other types are going to be more likely to impact within subjects design. And mixed subjects design, sometimes it's, well, now I've got all the threats. But interestingly, as we'll see, sometimes using a mixed subject design can help you account for some of the threats to internal validity. Again, we'll see that in a minute. Again, like I said, and this is all kind of an ideal people-free world where everybody was identical or they were all consistent. You could be confident using these research designs. But again, you can't, because you can't really obtain two identical groups. And you also can't eliminate every possible extraneous influence. You can't account for every possible alternative explanation, because other things are going to affect participant scores other than the independent variable. You can, however, take steps to reduce the influence of the threats to internal validity. But again, you can only take these steps if you know what the threats are. So let's. The first one we'll talk about is selection bias. This exists when groups, again, kind of thinking about between subjects design, groups that receive different levels of the independent variable are different on the dependent variable before the independent variable is introduced. And really a better term for this might be assignment bias, because it's really about deciding who will receive the level of the independent variable, not who will be selected into the study as a whole. When you're doing that, when you're selecting people to participate into the study, if you do that in a biased way, that's sampling bias. And sampling bias has a greater impact on external validity than on internal validity, and we'll talk more about that in the future. So this selection bias is really, again, maybe better thought of as assignment bias. One way you could go wrong is allowing for self-selection or self-assignment. Right? Letting participants choose what level of the independent variable they want to receive. Never do that. That's a bad idea. Imagine doing a smoking cessation study, right? Where you let people choose which group they want to be in. Right? Do you want to be in the group that's going to get their treatment to help you quit, or do you want to be in the control group where you don't get the treatment to help you quit? Right? If we do that, and we then compare people at the end, what are we going to see? Hey, our treatment worked. Right? Oh, good, the treatment must be really good. Yeah, maybe, but maybe people who really wanted to quit elected to be in the treatment group, and people who weren't ready yet, weren't at that kind of stage of change yet, opted to be in the no treatment group. Right? So maybe those groups were different in important ways other than the independent variable. And so then we have a serious threat to internal validity, and we can't really be confident that that group difference on how much they're smoking, which is our dependent variable, is due to the treatment or is due to how motivated they were to quit. Right? So how motivated they were to quit ends up being kind of this confounding factor, right? And a confound is just a variable where there's a difference across groups other than the independent variable. Okay. Another way you could mess things up would be selection from existing groups. And overall, you always think, well, random assignment's good, so I'll randomly assign, but I'll randomly sample from one group into the treatment condition. And this may happen, say, if you're maybe you work at an outpatient clinic where there are some clients that you have access to, where you could modify their treatment, right? And say, okay, well, I only have 50 patients that I can access. I need all of them to be in my treatment group because I need a large treatment group. So I'm going to randomly sample from those 50, 30 of them to be in the study. I'm using random assignment, that's good, right? And then I've got a friend that works at another clinic across town that I can't really manipulate their treatment. They'll get kind of the standard of care treatment, and I'll randomly sample from them as well, and then see I've got random samples, right? Well, no, not at all. The people at the two different clinics might be different in important ways before you've manipulated the treatment. Right? So if you select from existing groups differentially, you select, your group participants to be in the treatment group from one place or in one method, and you select people for your control group from another place or another method, well, now they're going to be different. Same thing if you do, if you recruit people to be in your treatment face to face, and then you recruit your control group over the internet. You're selecting from two different populations. So it's probable, definitely highly possible, that your groups are going to be different already before you do whatever it is you're going to do to them, which completely erodes your internal validity. Okay. So usually the gold standard here to prevent these things, so instead of allowing for self-selection or selecting from existing groups, is to use random assignment. Right? This is the most effective way to deal with selection bias. And random assignment, make sure we're clear, is not the same thing as random sampling. Right? Random sampling is about getting people into the study in the first place, where you have some population, and every member of the population has an equal probability, equal chance of being in your study. Selection bias has nothing to do with that. You could have a non-random sample, where you have, okay, I got the people in this one clinic who I can do stuff to, and they're going to be in my study. As long as you take all those people and you randomly assign half of them to be in the treatment group and half of them to be in the control group, you're good in terms of selection bias. Because again, it's not about selecting people into the study, it's about selecting them into one level or the other of the independent variable. It's about assignment. So random assignment keeps you from allowing for that self-selection bias. You're doing from one total group from the whole sample, so you don't have the existing groups problem. And ideally, random assignment will create fairly equal or equivalent groups. Right? Because again, if I'm doing a treatment study, trying to treat depression, and I'm going to select people into get the treatment and to be on a wait list, I don't want people in my wait list group to be more depressed at the beginning than people in my treatment group. Right? And the hope is, with random assignment, you'll get equal numbers of severely depressed people in each group, and equal numbers of moderately depressed and mildly depressed in each group. The thing is, random is random. It's not guaranteed. You won't necessarily get equivalent groups. The larger the group you have, the more people you're using, the more likely is that using a random assignment procedure will lead to equivalent groups. Right? With smaller samples, randomness has less a chance to lead to equality. Right? Think about if your study was, ridiculously small, 4 people total, and you had 2 people in one group and 2 people in the other. And if you had half of the people in the total sample were severely depressed and half of the people were mildly depressed, well, what are the odds that both severely depressed people could be in the same group and both mildly depressed people could be in the other group? Pretty good, right? Now, if I had 1,000 people, half are severely depressed, half are mildly depressed, what are the odds that all of those people that are severely depressed being one will be randomly assigned to the treatment group, and all the mildly depressed will be assigned to the other? Not as good, right? Randomness has a chance to work. So random assignment is good, but it's not a guarantee. So one thing that you can do is kind of check on whether random assignment worked. And this involves, once you randomly assign people to 2 groups, measuring if, in fact, they are equivalent. Right? So you may not measure them on the dependent variable, because maybe you're worried about measuring that too many times, but you measure them on some other important variable. And this might also be done after the fact. You might say, okay, well, I use random assignment, and there turned out to be equal numbers of women and men, equal numbers of people from this type of background. Right? So often you collect this kind of demographic information, and you can look after the fact, did the groups in fact appear to be equivalent? Did random assignment seem to work? Or again, that's kind of an after the fact thing. If you don't want to just kind of cross your fingers and hope that it worked, another approach you could use is matching. Right? And this is where, instead of leaving to chance, you measure people on important variables, the variables that you think are important, in terms of, I want these groups to be the same on this. And it may be the dependent variable, that's probably one of the things, but there may be other things too, right? If we are looking at some sort of cognitive treatment for depression, I want my 2 groups to be fairly equal in levels of depression. But I also want them to be fairly equal in terms of maybe IQ or cognitive ability. So I get kind of really one group that has really low verbal skills, then cognitive therapy may not work as well with them. So I might measure IQ as well, and I want to match people on IQ. So you think about all the variables that are important for the two groups to be similar on. The dependent variable usually being one of them, but there are frequently others. And then you say, okay, I'll get say it's depression and IQ things I'm looking at. So I'm going to find somebody who's really depressed in this group, somebody who's really depressed in this group. I've got maybe a pool of those, and then I'm going to say, okay, also within that group, somebody who's high IQ, somebody else in the other group that's high IQ, and now I've got this pair of people that scored similarly on depression and IQ. And once I have my pair, I randomly assign one of them to treatment and one of them to control. And then I go back and I do it again. I find another pair of people that are similar. And so I'm statistically matching people on important variables and then randomly assigning them to one group or the other. And this can increase the likelihood that your groups are similar. And it may be important if you have a small sample size, and then there are some really important variables that, well, you really need people to be similar on these variables in this study. Otherwise, you're not going to know what to conclude at the end. So you say, well, that sounds good, right? And it does work, but it does have its own problems. Right? One, you can't match on every important variable. In fact, the more variables you add to try to match on, the more complicated it gets to try and match, even with those two variables. Okay, I've got to find somebody that's similar on both of these things, because you might find two people that are both severely depressed. They're the same on that, but one has high IQ and the other has low IQ. Okay, they're not a pair. Let me look again. Right? Again, the more variables you look for, the harder it is to find matches, the more complicated it gets. So it's hard to do that, and also, you can't match on every possible important variable. Right? So even if you match on some important variables, the groups might still differ on other important variables that you didn't think of or just ran out of kind of statistical power to account for. Two, just because two people, think about these kind of pairs, are similar when you do this kind of initial testing, doesn't mean they'll stay similar. Right? They may look different on these important variables later, even if you hadn't given the independent variable to one of them. Right? And this is more true for variables that can be expected to fluctuate than more stable ones. So I'm maybe matching people on mood. Okay, everybody that's in a good mood to be paired, and then that's why I have equal numbers of people that are in good moods and bad moods in both groups. If I do that on Monday, and I don't then bring the groups back till Friday to do my study, where I'm going to do something to probably manipulate their mood, well, my pairs might no longer be equal. Somebody, I have this pair, both people were in a good mood on Monday, and I go back on Friday, one of them's now in a bad mood, the other one's in a good mood. They're discordant, they're no longer matching. Now my groups may not be equal, right? So just because I established them equal at one point in time, doesn't mean they'll stay equal. 3, this extra testing may have an effect on how participants perform on the measurement of the dependent variable. And we think about things like fatigue effects and practice effects. So especially if you're measuring them on the DV, I'm asking about the depression. Now, I'm going to ask them about depression again later. Asking them now may affect how they answer later. Right? So we have fatigue effects, practice effects, which are more about kind of ability measures, like how quickly can you recognize this letter, that type of stuff. They may get tired of doing that and do more poorly if you're doing it the same day, or they may get better at it and do better just because you've measured it more. There may be kind of sensitization effects where, okay, now I know what you're looking for, or you've activated in my mind that I should be thinking about this particular thing. I've activated that schema. You may be introducing demand characteristics where now they're going to be more likely to guess your hypothesis because you've asked about these things, so they know, okay, oh, this is probably a treatment looking at this. And if it's important for you to disguise your hypothesis, it may be hard to do if you use a matching design. And lastly, the fourth thing, it obviously takes more time and money to do this, to do matching. So random assignment is probably the most commonly used thing, unless it's super important to be confident that your groups are fairly equivalent, and again, you have a small number of people. Okay. The second threat to internal validity to talk about is maturation. And this is really only concerned for studies that have a pre-post component, so either a within subject design or a mixed subject design, because this is about changes from pre to post that are due to biological maturation or just variability over time. The idea that if I'm going to measure depression now, do my treatment for 6 months, and then measure depression again. So, okay, wow, after the treatment, everybody was less depressed. Okay, well, might they have been less depressed without treatment? Might depression actually get better? Yeah, actually, as it waxes and wanes, right? So we expect people that come in depressed to be less depressed later on. The degree to which the maturity is a threat depends on a couple things. One, the length of time between measurements between pre and post. Obviously, the longer the length of time, the more time you give maturation to have an effect, the more it can interfere with your ability to conclude that the effect is due to the independent variable. So longer running kind of longitudinal studies, this may be more of a problem. Another thing that I've kind of alluded to before, it depends on the stability of the dependent variable. Is the thing you're looking at, would it be expected to change due to maturation? Or is it something that's expected to be pretty stable? So if you don't do anything to them, we expect it to stay the same. Right? So like depression, we expect that actually to change across time. People to become less depressed and then more depressed, if it's kind of cyclical nature, versus in adults measuring IQ. It's thought to be pretty stable. Right? So if I measure it now and I measure you a year from now, your IQ should be pretty similar. Okay. And if I have something that boosts IQ, then I'm not that worried about maturation. If I find a difference, I'm pretty sure it's what I did to you, because I expect IQ not to change a lot for adults. If I was looking at the same thing in kids, I might be a little worried. And this has more to do with not so much that IQ increases in kids, but our accuracy in measuring IQ increases as kids get older. It's hard to measure IQ really accurately in young children, especially infants. And so what I think their IQ is pre to post, when I look at pre, I might be wrong. There will be a lot of error variance in that measure. So when I look at post, I may see a difference. And it's not because of anything I did. It's because now I have a better idea of exactly how smart they are. Okay, so you can use a shorter period of time. You can try to look for a DV that's stable if you're worried about maturation. The other thing you can do is use a mixed subject design. So this is where mixed subject design may help solve some problems rather than introduces them. So this may help you kind of parse out maturation effects. So imagine you have two groups, experimental group and control group. And you measure them both at time 1. You get a pre-measure on both groups. And then you do something to one group, but not the other, right? So you manipulate the independent variable for one group, your treatment group, your experimental group, and you don't manipulate it for the other, the control group. You do nothing to them. And we measure everybody again at time 2. I get 2 group means at time 2. Well, if I want to know, well, what was the effect of maturation? I look at how big a difference was there for the control group across time. And if the difference pre to post for the treatment group was bigger than the difference for the control group pre to post, then I'm fairly confident that my independent variable had an effect. So I can see what's the effect of the independent variable above and beyond the effect of maturation. And if so, I might see, well, time 1 to time 2, my treatment group, they got better, yay! And it's a big difference. That's good. But if it's no bigger than the difference for people who didn't get the treatment, then I can't be sure the difference is because of my treatment. It very well may be, and probably is, because of maturation. Okay. The third one, selection by maturation interaction. This happens when you don't use random assignment at the beginning, but somehow manage to get equivalent groups, at least on the dependent variable, before the IV is introduced. So maybe if you're using a matching strategy, but to try to establish equivalent groups. So okay, I didn't use random assignment to make them equal. I tried to make sure they were equal by matching. And so at time 1, they look the same, right? there's the difference between groups. There's not one. But due to maturation over time, the groups might differ, and they might be different even if you hadn't introduced the independent variable. This is kind of what I talked about before with kind of a problem of matching. Sorry, the problem of matching is this selection by maturation interaction where, okay, even if we establish them as equal, a week later, 2 weeks later, if I hadn't done anything to the variable, they might be different. That's kind of the idea of that, you know, I got a pair they're both in a good mood, and then a week later when I'm about to do my independent variable, one's in a good mood, one's in a bad mood, they've changed, and not because of the IV. I haven't done the IV yet. That's a selection by maturation interaction. Okay. The next one, regression effects. This is about regression to the mean. And again, this is more of a problem for something with a pre-post component within subject design. If you recruit people into your study based on extreme scores, right? So again, I'm going to have one group of people at time 1 and that same group at time 2. So if I say, hey, please be in my study, but you can only be in my study if you're really high or maybe really low on this variable. So I'm going to do this treatment for depression, but to be in the study, you have to be really depressed. You have to score above a 27 on the Beck Depression Inventory. Right? Otherwise, you don't qualify. That's my inclusion criteria, exclusion criteria. If I do that, if I get people only with extreme scores, you're probably going to see changes pre to post due to regression to the mean. Right? The initial score that is used to choose them to be in the study, at least part of the extremeness of their score, because it's extreme, probably due to random error. So maybe their true score was a 25, and then random error is going to drive them up or down, up to 27, down to 23. People who were really a 25 and were driven down to 23 aren't going to be in your study. People who are 25 and were driven up to a 27 due to random error will be in your study. Right? And if their true score is a 25, then the next time you measure them, again, their score will be somewhere between 27 and 23. So it may go down to a 23 just due to random error. So now you've gone from 27 to 23. It has nothing to do with what you've done. It's just because you picked somebody who was high, and high scores tend to regress to mean. Very low scores tend to regress to some other mean. Okay. Because you can't expect random error to push their score in the same direction the next time. So, the true score is 25. It got pushed to 27 now. When I measure them again later, if it's really random error, by about halftime it'll push that score up to 27 again. By halftime it'll push it down or not even halftime, but it may push down to 23. It may leave it at 25. Maybe anywhere in between. But it's probably not going to be above 27. It's not going to go up, right? Because they're already at the kind of extreme end. This kind of thing happens sometimes with applied research because clinicians are wanting to find out how to help people with the most severe problems. So it's not necessarily they're trying to get these regression to mean effects. It's just, okay, we're looking to help kids who are really aggressive. We're looking to help people that are really anxious. Well, if you only measure the really anxious, the really aggressive, and you're doing it across time, they're bound to be less of that when you measure them from time 1 to time 2. Again, this is where the mixed subject design might come in and be helpful. Instead of having one group pre and post, if you have 2 groups and you're using again the extreme scores, and you do something to one group and not to the other, if it is regression to the mean, you'll see the group that didn't get treatment also regress and look like they're getting better. And then you'll say, okay, well, it wasn't my treatment. Everybody regressed to the mean. Okay. So you can kind of see that effect. The other thing is to get a wide range of scores on your time 1 measure of the dependent variable. So don't set those inclusion exclusion criteria to only have extreme scores. Allow people who have some moderate scores, get some variability. People with room to go up or down. Otherwise, you're gearing it up to where, they're probably all going to go down. Okay. Next one, mortality, also referred to as attrition, people dropping out of your study, possibly by dying. That's what's called mortality, but not usually about dying. This is really only a threat to internal validity, if you have differential attrition, right, where people drop out more in one group than the other. Because if equal numbers of people drop out of their treatment group and your control group, and those people dropping out were similar, then your groups are similar. But if you get a different amount of people dropping out of one group than the other, or people get dropping out for different reasons, well, now my groups are no longer equal, right? And I have to have equal groups other than the IV. Now they're different because some have dropped out. That's a problem for internal validity, including that I have an effect. So what can you do about that? Well, sometimes not much. I encourage people to stay in the study, obviously. But the other thing you can do is examine the data from the dropouts, right? Look at who dropped out and see if you can figure out maybe why they dropped out. It can help you figure out what to conclude. And if mortality is something you're worried about, it's probably a good idea to plan to collect data at multiple points in time. So not just pre-post. So if you're going to do this kind of longitudinal study that's going to last a year, you don't want to collect data time one and then wait a year and come back and do it again, because people are going to drop out over that long period of time. So you want to have maybe a year, 3 months, 6 months, 9 months, and then a year. That way, at 3 months, maybe some people dropped out, but some people are still in, and then some of those people will drop out later. But at least you have some data on them, and you can kind of maybe have a better idea of why they dropped out. Okay, well, at 3 months, these people weren't doing very well, and all the people who weren't doing very well dropped out of the study. Okay, then that's important. If they weren't really, if people that dropped out at 6 months weren't different when we look back at 3 months, if they weren't different from anybody else back then we're less worried about the effects of mortality. But if they were different in important ways, then yeah, it's a threat to internal validity, and you have to kind of explain that in your paper. Okay, the next one, history effects, which again, one of those things that's really only concerned for pre-post designs, design with a pre-post component, in terms of threat to internal validity. Anyway, this is where something in the participant's environment has changed from pre to post, other than the independent variable. So from the time you measured the DV once, and then measure it again, you're going to manipulate the IV, but something else happened in that interim that causes a change on the dependent variable. So if you were doing a study back in 01, and you were measuring anxiety, and you did a treatment for it, but then then you measured anxiety again, pre and post. But between your pre and post, we had the collapse of the towers, 9/11. Well, we're going to see some changes in anxiety that have nothing to do with your treatment. It may look like your treatment caused people to become more anxious. Right? It probably didn't. There's this history effect, where there's something else that happened in the world, and at least in the worlds of these participants, that caused them to be different across time, and that they all shared. It's kind of the shared history. It can be major things like that. It can be minor things. Imagine maybe you're studying an intervention to stop bullying in schools. Right? So you measure the amount of people who are being bullied. How much have you been bullied? How many swirlies have you gotten this week? You do your intervention, and then you measure bullying again. You find a difference. Hey, yeah, my intervention worked. Maybe what happened was football season began, and the people who were doing the bullying are now too busy to bully people because they're at football practice all the time. Not to pick on football players, but I thought it was a good example. So what can you do about history effects? Invent a time machine. Go back in time and eliminate them. Beyond that, there's really nothing you can do. It's just something you have to think about, be aware of. And again, the longer the amount of time, the more likely this history is going to have an effect. The longer amount of time between your pre and post. So if you're doing these kind of long longitudinal studies, you have to consider what possible history effects could there be. Okay. Few more here. Testing effects. This one, again, for more pre and post. When testing at time 1 has an effect on performance on time 2 testing. Okay. Things I've alluded to just a little bit already. Practice effects, where people get better on the measure of the dependent variable, not because of something you did, but because they've had another chance to try and answer it. So this is more for performance-based stuff. How quickly can you hit this letter when something pops up on the screen? how well can you use I statements when expressing your feelings to your partner, right? So you may have that. You measure how well they do it. Okay, I want you to make I statements to your partner. They try it. You do an intervention, teach them how to do it, and then you measure it again. Well, there may be some improvement just because they tried it the first time. Oh, I never thought about doing that. So just it being measured, being asked to do something, might make them get better at it later, and your intervention had nothing to do with that increase. So they might get better. The opposite side of that would be fatigue effects, where people having to do, again, kind of performance type measures in the DV get worse pre to post because they're tired of answering questions. And again, that's stuff that happens more often with kind of cognitive research and things like that. Catching on effects. Measuring things multiple times, doing pre-post, makes it harder to hide your hypothesis. Sometimes it's important. Sometimes you don't want people to guess what you're doing because you're afraid that they're going to pick up on those demand characteristics and try to help you out, right? Consciously or unconsciously. So they might figure out the right way to respond. So you may be introducing demand characteristics by testing more than one time. And obviously, the more you test, the more they're going to figure out, oh, I know exactly what you're doing. Okay. So it just depends on if that's important or not to you. There's some studies where it doesn't matter if they know like that. Well, it's fine that they know that, yeah, we're looking at to see if this treatment works, and we think it does work. Okay. Instrumentation. This is the idea that it's possible that you measure the dependent variable differently at time 1 versus time 2. It could be something really obvious. Well, at time 1 we used this measure of depression, and then 10 years later there was a new measure that came out, and so we didn't want to use an old measure, so we used the new one. Well, now you're comparing apples to oranges. So a difference on level of depression might not be due to what you did to them, but it might be due to the way it's being measured. Right? So that's kind of an extreme example. The less extreme are things that are done maybe unintentionally, and maybe because the experimenters really want to see significant results. And this is more, I'm thinking along the lines of if your DV is something where there's observational data. So maybe you're watching kids on a playground, maybe you did your bullying thing, and you're trying to see, is there bullying present or not? So time 1, you're counting how much bullying is there, and then at time 2, and you had this kind of clearly defined level of, okay, bullying is when this happens. Time 2, now after doing your intervention, maybe that same thing happens that you would have called bullying at time 1. Time 2, you're like, well, that's not really bullying. It looks a little different. Right? So now you're applying the rules differently because you want to see an effect. If you're applying the rules differently in your observational coding, you're measuring the DV differently. So it could be because of that. It could be because, especially if you're using other people to help you collect data, they have fatigue effects or maybe practice effects whenever they're making observations or recording data. So they're either getting better at measuring the DV from time 1 to time 2, or they're getting worse at measuring the DV from time 1 to time 2. Either way, that could lead to instrumentation effects. So what do you do about that? Well, you standardize your measurement as much as possible. Right? So you have very clear rules for how things are going to be measured. You train people on measuring things, and then you check to make sure that they know what they're doing before you let them do it, which is going to involve maybe some pilot study. The other thing you can do after the fact is some spot check on your measurement. So you go back and you have your data, and you say, okay, well, whenever this so maybe you're doing kind of observational stuff, but hopefully you video recorded the observations. So you don't go back and look at every piece of data and make sure that they were coded appropriately. You randomly select certain things. Okay, in time 1, when they're measuring this, did they apply the rules appropriately? Yes, okay. Did they apply the rules appropriately again at time 2? And you'll spot check, randomly select a couple of instances, and if there's not a difference between time 1 and time 2 and how they're applying the coding rules, then you're good. If not, you worry about instrumentation taking away from your internal validity. Okay, the last threat I talk about is really just a catch-all category here. Low experimental control, kind of other confounds. Right? Remember, a confound or confounding variable is any variable that's different, that differs between groups, between levels of the IV, other than the independent variable. So if you exert low levels of experimental control, your groups might have different experiences in a way that's not related to the IV. Right? Imagine if you brought a group in for, if you were studying a treatment for social phobia, and you're looking at a group that gets individual therapy versus a group that gets a wait list. Imagine you brought everyone in the study in for individual therapy on the same day, right? And then kind of walk with me on this scenario here. Imagine these folks meet each other while sitting in the waiting room. Now the group that gets individual therapy also gets a chance to socialize with similar individuals struggling with similar problems. Okay. This experience is different than the control group, and that socializing isn't part of individual therapy. It happened to be part of your study, but it's not. Your IV was individual therapy. It wasn't individual therapy plus social hour. Right? So then these two groups differ other than the IV. So if they're different later on the dependent variable, which is probably social anxiety, you can't be sure it was because of the individual therapy. It might also be because of kind of that waiting room socializing. Right? That's an alternative rival hypothesis, another possible explanation that you didn't account for because you didn't exert experimental control. You didn't try to make sure that the experiences were identical except for the independent variable. It can be things like that. It can be the time of day that testing of the dependent variable occurs, the conditions, the attitude of the experimenter, if they're smiling or not smiling, so many different things, and it's hard to control everything. But the more things you can control, the greater your internal validity. Right? So if you bring people into a lab and you have videotaped instructions, there's lots of things you can do to kind of standardize your intervention to where it's okay, everybody gets the same exact thing except for the IV. There are things you can do that will increase your experimental control. And when you do that, you do increase internal validity. But that may cost you elsewhere, which we'll talk more about later. Okay, kind of review. The list we're talking about here is not exhaustive. It's not every possible threat to internal validity, but it's some of the major ones. Other threats to kind of just be thinking about in the back of your mind. If you have poor construct validity, right? So if the things you're measuring, your dependent variable, or the things you're manipulating, your independent variable, if you have poor construct validity there, then you can't have good internal validity. Right? So if I think, this therapy causes a decrease in depression, but if I measure depression poorly, if I didn't measure it in a way that really reflects the truth of what depression is, so I have poor construct validity, even if I find a group difference, I can't be sure that the therapy causes a change in depression because I didn't measure it well. Right? I had poor construct validity. Right? Or if my treatment had poor construct validity, same problem. Right? So there's those kind of things. Using the appropriate data analytic strategy, right, may impact your internal validity. And there are all kinds of choices you make when running your stats in terms of, using this correction or that correction, using this model or that model. And those choices may have an implication on the degree to which you could draw cause-effect influences. And usually those choices are driven by what your data look like. Right? Because most statistical tests are based on, well, if the data are perfect, if they're normally distributed, and you have similar amounts of variance in all these groups, then these numbers will tell you some truth. Unfortunately, data aren't always the way they should be, and so we have all these weird correction things. So there are other threats that we didn't get to. We've covered the main ones. Reduction versus elimination of threats. Reduction is probably more realistic. You try to eliminate as many as you can, but ultimately we recognize that we can't eliminate every possible threat. And that's why we work in this very kind of probabilistic model in science, where we find an effect and we conclude that this thing probably has an effect. So no one study can be used to say, this definitely affects this. Everybody should do this now. That's why we require replication. Multiple studies have to converge. Right? We have to have similar findings across different studies with different groups of people, different ways of looking at the same relationship before we get any kind of real confidence that there's a cause and effect relationship between two variables. And that's because we can't eliminate all the threats to interoperability. The last thing to think about, as I started to allude to there a little bit before when talking about confounds and exerting high experimental control, be thinking about what the impact is on external validity when you do things to increase or strengthen your internal validity. There's typically that trade-off. So think about, particularly for experimental control, the more you control people's experiences, put them in a lab, make them watch a video, make everything the same, to what degree can the relationship between variables you find in that type of study be generalized out into the world? Okay, these two variables are related in the study. Are they related elsewhere, in other situations, other times, with other people? Okay, that's all for